Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this video is on random forests. It's part of a course, Analytic Methods for Lawyers. So, random forests are a durable and powerful algorithm for supervised machine learning. They have the advantage of working whether your task is classification or regression, sometimes called prediction, and what it's designed to do is essentially compensate for some problems with decision trees. Decision trees are lovely, but they tend to overfit the data. And so the idea here is to build up an ensemble of trees, and each tree is denied information in two different ways. First, generally speaking, the data is bagged for each tree, meaning that it doesn't see every single data point, and you can refer to the prior video on bagging. Second, for each tree, every time a split is made in the data, you don't search all of the features. Rather, you search a random selection of features. The result is that individually, the trees don't perform as well as, say, a full-fledged decision tree, but collectively, they exhibit low bias and high variance. They're very powerful and accurate. The main drawback, I would say, of random forests is that it's difficult to explain their results. Let's do a little review on the foundations that we'll need to implement a random forest. First, bagging. Remember what bagging is? You sample your data without replacement so that some of the items may not get picked. How many do you pick? Well, it's up to you. Generally, this fraction, which is like what 0.6 or something, what is that fraction? Let's see. Yeah, 0.63. You're going to sample about 63% of your data, and then you're going to fill out your data set by making it the same length as the original data. So you're going to have repeated elements, but the idea is that some of the elements that you might be incentivized to chase noise on won't be present in the bagged data. So I'm going to show you bagging again on the Boston Homes data. Let's go grab our Boston Homes data. We're done. And now let's run 100 different linear regressions. That is, even though I've been teaching bagging in the context of machine learning, it actually can work in good old statistics. So what we're going to do is we're going to put the data in the right form for statistics. Remember, Wolfram data comes in slightly different form when it's intended for machine learning and when it's intended for statistics. There are 13 variables in the Boston training data. For these purposes, I don't care what they are. We're not really interested in the substance of the Boston housing market. We're simply interested in looking at what does bagging accomplish. So I'll just list 13 basis functions, 13 variables. What am I after? I'm after the best fit parameters. Those would be the 13 parameters for each of the 13 variables, plus an intercept parameter. And I'll do this 100 times. We've talked a little bit about augmented terse before. It's a resource function that basically produces a short version of the output, plus generally the dimensions of the output. All right, so let's run that. And we're done. Pretty cool that you can run 100 linear regressions in that period of time. And you can see we have 100 by 14 matrix, 100 because we have 100 bagged data sets, 100 linear regressions, 14 because we have 13 variables plus the one intercept term. So now let's look at the spread of each of the parameters on the bagged data, and this will give us some idea maybe about what the distribution of those parameters might look like in the real world. We'll write a little function, feature histogram function. It's going to take a vector of numbers as its first argument, a list containing a single integer as its second argument, and it's going to produce a histogram of the distribution with a label. I don't think I need to explain string template to you at this point. You can probably figure it out on your own. But what's the argument? It's the value of the index minus 1, so that if the index value was a list containing 1, you would call it feature 0. And if the index value was a list containing 7, you would call it feature 6. So what I'm going to do next is I'm going to take my bagged best fit parameters that I computed up here. I'm going to transpose them so that instead of having the rows be all the regression coefficients for a single run, now the rows are each row 12, for example, is all of the regression coefficients for feature 12 throughout those 100 regressions. So instead of it being a 100 by 14 matrix, we're going to turn it into a 14 by 100 matrix. And then I'm going to run map feature histogram function over it. We haven't spent too much time on map index, but the idea is in addition to passing the argument, the value, to map, you also pass a little index saying what position in the list is this item. So that if we were to do map indexed f of ABC, this is what we get. Okay? F of A in 1, F of B in 2, F of C in 3. And by saying I want the first element of index, I'm basically this would turn into FB of 2 without the list, FC of 3 without the list. And you can look up map indexed in the documentation. I think at this point in the course, you'll be able to figure it out. All right, so we do that. And we get a bunch of histograms showing maybe the spread of values for each of the features depending on how the particular data has been eliminated. And it's kind of interesting to see that actually in this thing there does seem to be quite a substantial variation in the regression coefficients. All right, so that's the concept of bagging. Let's talk about the concept of decision trees. So in decision trees, what we tend to do is we look at all the features and we decide which split on which feature would improve the performance of the tree the most. And usually that's a binary split. So then we have a left-hand side and a right-hand side. And now we can do a decision tree on what's on the left-hand side, all the cases that went to the left-hand side. And we can do a decision tree on all the cases that went to the right-hand side. And now we've got 4 trees, or four clumps of data, not 4 trees, 4 clumps of data. And we can run a decision tree on each of those. And we keep doing it and doing it and doing it until some stopping criteria is met. How do we measure the performance of our split? Well, one way to do so is to look at weighted entropy. That's what we did back when we studied decision trees. And perhaps a little review of that is appropriate because this is one of the foundations of random forests. That is, random forests have decision trees as their constituent part, and decision trees make use of things like weighted entropy or other performance measures to figure out how to continue the recursion process as you keep splitting and splitting. We're going to be using our wine data that we've used before, where I turned this data, instead of having numbers from I think 4 to 9, we're just going to turn it into good wine if the wine has a score of 7 or better, bad wine if it has a score of 5 or less, and otherwise, which means a value of 6, it's fair wine. So we'll do that. Now we have our wine, and actually just to make things fast, I'm going to look at the first 50 wines. And what I'm going to do is I'm going to split the wine according to whether feature 4, and again, I don't care what feature 4 is. We're not really interested in wine at this point. We're interested in machine learning. I'm going to see, is the value of feature 4 for that bottle of wine bigger than or less than 5.05, which happens to be the median value. And so let's do that. We're going to use the map reduce operator resource function, which I believe we have seen before. But the idea is, just to refresh, you're going to split or group based on, you'll see there are 2 arguments here. There is a first argument, which is a rule, and a second argument, which is some function. So let's look at this rule. The left-hand side of the rule is some function. It's asking, is the first part's fourth part, or the fourth part of the first part, greater than 5.05. And the reason that we're doing the fourth part of the first part is just the way that Wolfram tends to store its or represent its data. So if I look at the first bottle of wine in the test set, it's a rule. And the left-hand side are the features, the right-hand side is the target. So if I say what is 1,4, I'm going to get 1, 2, 3, 4. I should get 12.9. Right. I want to look at the first bottle of wine, and then I want to look at its first part and the fourth part. There we go, 12.9. Okay, so this is what we split on. Then we take each of the bottles, as it were, that we've gotten as a result, and we apply a function to that. And here the function is I just want the second part. What's the second part? Again, let's look at our bottle of wine. The second part is, how good a bottle of wine is it? And so we'll end up with two groupings, and I'll show it to you here. We'll run this code. The third function, by the way, the second argument, I'm being too fast. The second argument to MapReduce operator takes a function and applies it to the groupings that have resulted from first the grouping and then basically the processing of each element in the group. And I'll do this on the first 50 bottles of wine. Identity, what does identity do? Identity does nothing. That's its job. Okay, so there you go. For bottles of wine for which this condition is true, the quality was fair, 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 bad, bad, etc. For bottles for which this grouping was false, the quality is fair, 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 bad, 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 good, good, fair, etc. Okay? And maybe you can see what MapReduce does even better if I use an abstract function like G here, and now the result is G, a fair, 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 blah, blah, blah. But identity just says, well, don't do anything. All right. So that's what MapReduce operator does, and we're going to use MapReduce operator to actually calculate the entropy of each of the classifications. And you may need to go back and look at the lecture on entropy, but basically it's a measure of purity. If all the wine is fair, then the entropy is 0. If all the wine is good, then the entropy is 0. If half the wine or a third of the wine is fair and a third of the wine is good and a third of the wine is bad, then our classifier hasn't done very much work. And so you're going to have a high level of entropy. And we're just going to compose it with n, which is going to give us the numeric value rather than some fancy thing involving logs. So let's do that. And we find that the entropy among the wines for which this condition is true is 0.63. And the entropy for the wines for which this condition is false is 1.039, blah, blah, blah. But what we want really is the weighted entropy. We want to know, okay, this is essentially the entropy of the group, but how many people are in that group? That is, or how many wine bottles are in that group? If it's just 2 wine bottles, maybe we shouldn't get too upset that the entropy within that group is high. On the other hand, if there are 100 wine bottles in there and the entropy is high, then we can say, hey, that split didn't really accomplish very much in trying to figure out the quality of the wine. So to do this, the only thing we have to modify is this reduction operator. This is the reduce part of MapReduce. And so we'll just take the length of the number, that's the number of bottles of wine in the leaf, and multiply it by the entropy. And again, we'll take the numeric value. So when we do that, now we find that the weighted entropy is 11.45 for those for which this condition is true, and it's 33.27 among those bottles for which this condition is false. And to get the total weighted entropy, we just add up those two numbers. And you may remember that the percent sign says just take your last output. So we can total that, and we get 44.7, which is 11.45 plus 33. We're going to be doing what I just did a lot, and so let's automate it. Let's write a function of weighted entropy that takes data in the machine learning format, a feature number, and a proposed split value. And it's really the same code that we had up here. We're just going to make it abstract. So instead of being 4, it's whatever feature you want. Instead of it being 5.05, it's whatever split value you want. And the rest of the code is the same. This is one of the very nice things about Wolfram language is you do something concretely, and then you kind of figure out what you actually did, abstract it, and turn it into a function. And by doing it that way, A, you're going to automate, and B, you're going to reduce the chances of making mistakes. So let's make sure, of course, that it does give us the same answer. And I guess I cheated and did this beforehand, and indeed it does. Good. Okay, so what I'd like to do is I'd like to plot the weighted entropy across all possible splits of the feature, of feature 4. So what we're going to do is we're going to take, first of all, we're going to find out what are all the possible splits. So I'll take our first 50 bottles of wine. I'll only look at their features, and then I'll look at the fourth part of all of them. So now I've got a bunch of feature 4 values. I'll delete the duplicates. I'll sort them high to low. I'll put them into groups of 2, just so you can see what this last part does. Let's do partition of 3, 4, 6, 8, 1, 10, 23. We'll partition it into groups of 2 with an offset of 1. And so you can see it's forming 3, 4, 4, 6, 6, 8, 8, 1, 10, 1, 10, etc. And then I could just map the mean over these, and then I'd get nice, convenient splitting values, because there's not going to be anything in between them. All right, so that's what this code does. It says delete the duplicates, sort them, group them into groups of 2 with an overlap of 1, figure out the means, and that's all the possible split values. All right, so there they are. There are 28 of them. Now what we're going to do is we're going to make a table. We're going to say take all possible split values and compute what is that split value and what is the weighted entropy on feature 4 given that split value. So there we go. See how it works nice and fast? We get a something we can plot. So let's plot that. And what we see is that the weighted entropy seems to be lowest if we're splitting, I don't know what that is, maybe like 3.5 or something. And we wouldn't do as well if we split at 10, or certainly if we split at 19. So this process gives us an idea about the optimal split for feature 4. But we don't want to just look at feature 4. We want to look at all the splits of all the features. So we need to automate further. Let's write a function called allSplits. This does basically exactly what I did before. It takes your data, it finds the feature in question, deletes the duplicates, sorts, partitions offset 1, and figures out the mean to get all the splits. All right? Now, the next piece of code, which you're going to see someplace down here, the next interesting piece of code is going to use this flatten function. And we haven't seen much of flatten before, so let's take a look at flatten. Okay, here's the simplest form of flatten. I've got lists that have nested lists inside, and I want to say flatten. So what it's just going to do is it's just going to unravel every single one of these nested lists. So now it's just one list, and what's the order? The order is exactly the same as it was here if I basically took out all of those curly braces. So that's what flatten does. There's a more advanced form of flatten which has a second argument, and it says I'm not going to flatten out every list. I'm going to start at the top and denest, basically delist things as many times as you've told me to do so. So if I do this, see how these had 3 braces here? And so now, and there are 2 braces here. So now, instead of there being 3, there are 2 here. And instead of there being 2 here, there's 1 here. And then all of these are basically turn to 0 braces. So that's what flatten with a second argument of 1 does, and that's the little thing we're going to need as part of our functionality here. All right, let's look at performance by feature. So here's the concept. We have data, we have a feature, and we have some performance measure. Maybe it's weighted entropy, maybe it's sum of the squared residuals, who knows. And we're going to say compute all the possible splits of that data for that feature, and now make a table for every such split. What feature are you using? What's the split value? And what's your performance measure? What does the performance measure need? The performance measure needs the data, the feature, and the split value. Right? So now we can implement this. Let's do performance by feature. Here's our data. What's our feature? Well, our feature is going to vary from 1 to 11. And what performance measure are we going to use? We're going to use weighted entropy. And then at the end, we're going to flatten 1 this. And you'll see when we do the augmented terse what the resulting shape of the data is. Okay? So we are, all right, we're done. And you can see we have a 284 by 3 array, and that's exactly what we want. We have for each feature, for each split value, what is the weighted entropy? For each feature, for each split value, what is the weighted entropy? And then, if we want to find the optimal split, we just say, well, would you please sort those and give me the first one, because the first one will have the lowest weighted entropy, and we want entropy to be low. So we do that, and it turns out that splitting on feature 8 at value 0.99325 produces the lowest weighted entropy. So that's essentially how decision trees work, and they just do that recursively. That is, now that we've done that split, now we'll find out, hey, in each leaf, now what's the optimal split? Okay? Let's go to random forest. The review's over. Onwards. All right. Supposing here, instead of giving every single feature a chance to be the best, I was picky. And I said, I'm only going to give a feature a chance if it's feature 1, 5, 7, or 12. So I'm going to take from our table only those in which the first value, that's the feature, is 1, 5, 7, or 12. Member Q is basically, is it a member of? And we're going to then sort the resulting elements, and according to the last value, which is the weighted entropy, and then I'll pick the best. All right, so it turns out that if I'm limited to 1, 5, 7, and 12, the best thing I can do is to split on 5 at a value of 0.041, and I'll get weighted entropy of 41.67. But I don't want it just for this subset of data. I want it for every subset of data with length 4. So I'm going to form all the length 4 subsets of the set 1 to 11, and then I'm basically going to run this exact same code. So I do that here. And then when I'm done, I'm going to see how many of each, like maybe there are 23 occasions on which this is the best thing. I'd like to know that. And then we'll sort them so that the splits that come up most often are seen first. So let's see what happens. And amazing how fast that is if you write efficient code. And it turns out that this split here, 8, comes up 120 times. This split at 11, feature 11 at 12.15 comes out 84 times, all the way down to this particular split, which only happens once. So the point is that every random selection of features to split on can generate a different split. And then, since the leaves are different, and now you're going to select new random features, again, the splits will be different. And so, every tree is very, very likely to be unique. and because it will be the consequence of different sets of restrictions imposed at different times. The other thing I should tell you is that although there are some algorithms that don't make use of it, oftentimes you also make use of bagging. That is, not only do you split differently, but also the data that you start with has been bagged. Although, and as I understand it, in its original conception, random forests did not involve bagging, but I guess they found that it worked a little better that way. Okay, so I just did it with decision trees where our performance metric was weighted entropy, but we can actually do it for regression trees as well. Regression trees are really the same thing as decision trees, except the performance metric is different, and a very common performance metric is the sum of the squared residuals, where the predictor for each leaf is the mean value of the target in the leaf. So that if the values in a particular leaf, the targets are 3, 5, and 7, well, the mean is 5, and the residual of the first thing is 2, or -2, and so that squared is 4, and the residual of the second one is 0, because 5 is the same as 5, and the residual of the third one is 2, and that squared is 4, and so the sum of the squared residuals is 8. And so what I want to do is to compute the sum of the squared residuals in each of the leaves and find the split that minimizes the sum of the squared residuals. So all the code is really the same. Here's our only little difference. Instead of weighted entropy, I'm going to say regression tree SSR, and this is our friend that's going to calculate the sum of the squared residuals. It's making use of our very familiar power total resource function at this point. So we'll evaluate that. And then this is exactly the same code as I had up here, right? Performance by feature of this. And so again, we will run performance by feature. This time there are 13 features. We're going to use the Boston training data here, not the wine data. And we're going to use our performance measure of regression tree SSR. So let's run that. Bumpity dumpity dumpity. And it is okay. We have a 2020 by 3 array. Again, what are the elements of that array? Well, let's look at this one. This is saying if you split on feature 13 at a value of 29.805, the sum of the squared residuals are 27,310.2, whereas if you split on feature 1 at a value of 0.02182, then the sum of the squared residuals is 28,499.1, so this one is not as good as the first one I showed you. And again, we can find the optimal split by just sorting these results by their last value, sum of the squared residuals, and then taking the first value in the sort. And so it turns out that what we should be splitting on is feature 6 at a value of 6.978, and that will result in a sum of squared residuals of 15,137. So that's done a very nice day's work. Okay, but in random forests, we're not going to get the choice of every single feature. We're going to tie our hands behind our back and restrict ourselves to a random subset of the features. How many? I'm going to pick 5. I'll discuss a little why that is. So I want to form every 5-member subset of the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then we'll do this same code of saying find me, if I restrict myself to that subset, what's the best split? And then we'll do counts, and then we'll do a reverse sort. And this turns out to appear the most often. Second most frequently chosen is split on feature 13 at a value of 7.865. And you can see it's pretty close. And that happened 330 times. So this is the idea of how a regression tree works with a random forest. Theory's over. Now let's see how it's implemented in the Wolfram language. And once again, you will appreciate all the detail that has been abstracted away. So here's how you do a random forest. You say, for a classification problem, you say classify. First argument's your data. Then you just specify the method. Hey, I want a random forest. And I'm going to shut off this reporting thing because I don't think it's useful in this circumstance. And then what we're going to do is we're going to take a classifier measurements on this generic random forest using the test data. And let's actually merge those two cells together. And now let's run it. And we're done. And we can see that our random forest got an accuracy of 55.7%. Its mean cross entropy is 0.9. And it didn't, you can see it didn't take very long to do that. So, great. Okay, so you might think, well, we're done. And in some sense, we are done. That was the whole thing. Maybe the video could have been a lot shorter, but then you wouldn't have understood what was going on behind the scenes. But let's talk about tuning a random forest, because how many trees are in the forest, right? So you can control how many trees are in the forest with the tree number sub-option. Here's how you do it. You say the method and you make a list. The first element of the list is the method you want to use, and then the remaining elements are various sub-options, of which we'll talk about a couple. So here we're going to make a 5-tree forest, kind of sparse, and we'll run classifier measurements, and let's see if just having 5 trees really does anything to diminish our accuracy in generalizing, and it does have some effect. We're down to 50%, so maybe more trees are better. Up to a point, and in fact in the exercises for this notebook you're going to get to explore that. The other thing you might want to control are the fraction of features that you look at. Like, do you want to look at 20% of the features each time? Do you want to look at 80%? There's no correct answer, but there's sort of our rules of thumb. And for classification, the rule of thumb is you take the square root of the number of features and you divide by the number of features. So if there were, 11 features, you take the square root of 11 and you would divide by, oopsie, that's going to get the division sign in there. You would divide by 11 and it would tell you to get about 30% of the features. And of course it may have to round when it actually executes that because you need an integer number of features presumably. For prediction tasks, the rule of thumb is take 1/3 of the features each time. But there's no exact right answer. Let me show you what happens if we violate this rule and we take 80% of the features. That is, we think, ooh, if we'd only give the random forest more information, I'm sure it would do better. So if we do that, what we find is this 53.7 is not as good, quite as good as when we did it originally, and it used its default value, which I believe Wolfram's default value, let's actually look that up in the documentation. I think it's 0.5, but I could be wrong. Let's look. And details and sub-option, feature fraction. Oh, it's got some complicated algorithm. All right. In any event, we can do an experiment. Let's do an experiment. Let's see how changing the feature fraction affects the mean cross entropy of the result. And my theory is that it's going to be a Goldilocks thing, where if the feature fraction is too low, it's not going to be so great because it's just not going to have enough data. If it's too high, it's going to chase noise, and so it won't replicate well on the wine test. And if it's somewhere in the middle, life will be great. So let's see. We're going to let our feature fraction go from 0.1 to 1 in increments of 0.1. We'll make a little table. Dumpity, dumpity, dumpity. And let's make a list plot of that just so we can see. And, well, I wouldn't make this a bedtime story, but you can see that this value in the middle here of 40% seems to do better, certainly does better than giving it a lot of information, and it actually does better than giving it too little. And so it is not always the case that providing more information to a classifier or something that metaphorically acts as a classifier will actually improve its performance because it may simply lead the classifier to chase noise. So, what's left? Well, we really ought to look and see whether this whole thing's worth anything. That is, maybe a decision tree. If we just did one decision tree right the first time, we'd get a good result. So let's see. Well, we're going to classify our wine training data. We're going to say use a decision tree. I don't need to know about the progress. And let's see what our performance looks like. And no, our accuracy is only 50%. On the decision tree, our cross entropy is higher at 1.04 than it was here, where we're down like at 0.88. So the decision tree is inferior to a random forest. And so one of the things you're going to explore in the exercises is, are there any costs? That is, it takes time to generate all these trees, and so you'll explore a little bit about the cost of computation. But what do we conclude? We conclude that random forests are cool. They perform very well. I think they're actually easier to explain than neural networks, which we'll come to very shortly, and you can decide whether I'm right about that. I think they're easier to explain than gradient-boosted trees, I'll tell you that much. And even though gradient-boosted trees have a little better performance where you're trying to squeeze out every drop, sometimes explicability of the algorithm counts for something. The one really bad part about random forests is, even though I can explain to you after, whatever it's been, 30 lessons, how to generate them, actually explaining to somebody why it scored them a certain way is very hard. Are you really going to say, well, the first tree, which was denied some data, first split on X, and then those two leaves split on Y and Z because they were denied certain data, and then there was another split. But in the second tree, which faced different data, it thought that you were in this category, and on, and if there are 100 trees, that's a very, very long story to be telling somebody who's angry because they weren't let out of prison, or they were denied cancer treatment because of some dopey machine learning algorithm, or at least that's what they think. So that's a drawback of random forests. It's actually a drawback of many machine learning algorithms, and we will talk about interpretability in a later lesson. But that's it on random forests for now. Hope you enjoyed.